Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The 1930 publication of Niels Bohr's The Theory of Spectra and Atomic Constitution offers a curated intellectual history, a set of 3 essays from 1913, 1920, and 1921, a document the birth and maturation of the old quantum theory. This collection is more than a historical artifact, it is a testament to a unique mode of scientific reasoning, one that operated in the liminal space between the coherent world of classical mechanics and the yet unformalized realm of quantum phenomena. This evaluation will proceed through a direct, section-by-section analysis of the claims, arguments, and conceptual frameworks presented within each of these foundational papers. It will assess the internal logic, the nature of the evidence marshalled, and the profound intellectual architecture Bohr constructed to render the atom comprehensible. The work reveals a mind grappling with fundamental paradoxes, employing a powerful blend of axiomatic fiat, physical intuition, and an unwavering commitment to empirical adequacy. Its claims are audacious, its methods provisional, yet its success permanently altered the course of physics. Section 1. The Foundational Postulates and the Hydrogen Atom. The first essay, originating from his 1913 papers on the constitution of atoms and molecules, advances a set of claims that are at once revolutionary and deeply conservative. Bohr begins by accepting the planetary model of the atom proposed by Ernest Rutherford, a dense positive nucleus orbited by electrons. His central analytical task is to address the model's catastrophic instability within the framework of classical electrodynamics, which predicted that an accelerating electron must continuously radiate energy and spiral into the nucleus. Bohr's solution is presented through 2 primary postulates, assertions whose validity derives almost entirely from the explanatory power they unlock. The first postulate posits the existence of certain definite stationary states for the atomic system. In these states, the electrons move according to the laws of classical mechanics, yet they do so without emitting energy radiation. This is a profound departure from Maxwellian physics, presented with the calm authority of a necessary condition. Bohr's argument for this claim is one of consequence. He provides minimal a priori justification, instead demonstrating that such a state of affairs is a prerequisite for atomic stability. The evaluation of this claim, within the paper's own terms, rests on its utility. It transforms the atom from a transient impossibility into a stable entity capable of possessing a fixed identity, a property essential for explaining the consistent nature of the elements. The second postulate governs the process of radiation itself. Bohr claims that the emission or absorption of energy occurs when the system undergoes a transition between 2 of these stationary states. The radiation produced is monochromatic, and its frequency is determined by a specific rule. The difference in energy between the initial and final states is equal to Planck's constant multiplied by the frequency of the radiation. This is the celebrated frequency condition. Here, Bohr massively fuses the quantum concept introduced by Planck for blackbody radiation with the mechanical structure of the atom. The claim's strength lies in its ability to account for the discrete lines observed in atomic spectra instead of a continuous smear of frequencies predicted by classical orbital decay. Bohr's mechanism generates a set of specific, predictable spectral lines, each corresponding to a permissible electron jump. The evidence he marshals is the known empirical fact of line spectra, which his postulate reinterprets with stunning clarity to make the framework computationally viable. A third crucial claim is introduced, a quantization condition that selects which of the classical orbits correspond to the allowed stationary states. Bohr asserts that for a circular orbit, the angular momentum of the electron is an integer multiple of a fundamental unit, specifically Planck's constant divided by 2 pi. This condition, which appears almost as a brilliant piece of dimensional analysis, is the keystone of the model's predictive power. It is an ad hoc rule, a quantum constraint imposed upon the classical system. The evaluation of this argument within the 1913 essay hinges entirely on its success in deriving the empirical formula for the hydrogen spectrum. Bohr proceeds to calculate the energies of the stationary states for the hydrogen atom and, using his frequency condition, derives the Rydberg formula, his theoretical expression for the Rydberg constant, constructed from fundamental constants like the electron's charge and mass and Planck's constant, matches the experimentally measured value with remarkable accuracy. This predictive triumph is the ultimate vindication of his initial, seemingly arbitrary postulates. The internal logic of the essay is therefore one of axiomatic deduction except these foundational claims, and the deepest puzzle of 19th century spectroscopy finds a quantitative solution. The work presents a model whose hybrid nature is its defining characteristic, a classical mechanical core regulated by externally imposed quantum rules. Section 2. The correspondence principle as a heuristic guide. The second essay in the collection, a lecture delivered in 1920, addresses a central conceptual challenge that arose from the success of the 1913 model, the profound disconnect between the quantum rules governing the atom and the highly successful classical laws governing the macroscopic world. The paper's central claim is the articulation of the correspondence principle, a powerful heuristic tool designed to bridge this conceptual chasm. Bohr argues that in the limit, where the quantum numbers describing the stationary states are very large, the predictions of the quantum theory for the properties of radiation must coincide with the predictions of classical radiation theory. This claim establishes a formal requirement for the consistency of the new atomic theory, ensuring a smooth transition to the familiar classical description in the appropriate domain. Bohr details the mechanism of this principle with subtle reasoning. In classical physics, the radiation emitted by a periodically moving charged particle, like an orbiting electron, can be decomposed into a series of harmonic frequencies, integer multiples of the fundamental orbital frequency. In Bohr's quantum model, the frequency of emitted light depends on the energy difference between two states, a concept alien to classical thought. The correspondence principle connects these two pictures. Bohr demonstrates that for transitions between adjacent high-energy orbits, the frequency calculated by his quantum rule numerically approaches the fundamental orbital frequency from the classical calculation. Furthermore, transitions between states separated by a larger integer difference correspond to the higher harmonics of the classical motion. The evaluation of this claim reveals its role as a discovery engine. The correspondence principle was far more than a simple consistency check. Bohr wielded it as a tool to deduce new quantum mechanical laws. He argues that since the principle must hold for large quantum numbers, the quantum laws governing phenomena like the intensity and polarization of spectral lines must be a full generalization of their classical counterparts. For instance, if a certain harmonic frequency is absent in the classical Fourier analysis of the electron's motion, then the corresponding quantum transition should be forbidden. This provided a rational basis for the so-called selection rules, which dictate which electronic jumps are allowed and which are suppressed. This argument gives a physical intuition to what were previously empirical observations. It allowed physicists to use their well-honed classical intuition to guess the correct quantum laws in a domain where formal theory was absent. An astute reader might perceive a certain intellectual audacity in elevating this beautifully reasoned piece of physical intuition to the status of a principle, lending it the gravitas of a law of nature. Its true function was that of a powerful navigational aid, allowing the theory to be extended from the simple hydrogen atom to more complex systems and phenomena. The claim's validity within the essay is demonstrated through its successful application to explain the structure of the Zeeman and Stark effects, where the splitting of spectral lines in magnetic and electric fields could be understood through a correspondence with the classical motion of the electron under external forces. Section 3. Architecting the periodic table. The third and final essay, based on a 1921 report, represents the culmination of the old quantum theory, showcasing its ambitious extension from the realm of single electron systems to the entire periodic table of elements. The work's central and most audacious claim is that the physical and chemical properties of all elements, as systematized by the periodic law, can be explained by the successive capture of electrons into the quantized stationary states of his atomic model. Bohr proposes a comprehensive architectural model for the atom, a theory of electron shells and subshells that provides a physical basis for chemical periodicity. The mechanism Bohr details as a conceptual building-up process, the Aufbauprinzip. He argues that one can understand the structure of a complex atom by imagining the nucleus with its large positive charge and then adding electrons one by one, with each electron settling into the lowest energy available stationary state. The novelty of his claim resides in the detailed structure he proposes for these states. He classifies them not only by the principal quantum number, n, which largely determines their energy, but also by a second quantum number, k, related to the angular momentum, which determines the orbital shape. This leads to the concept of electron shells, characterized by n, being composed of several subshells, characterized by k, the chemical properties of an element and determined primarily by the configuration of the most loosely bound, or valence. Evaluating the specific claims within this section requires examining how Bohr justifies the population of these shells. For example, he argues that the first shell, with principal quantum number 1, can contain a maximum of 2 electrons, the second shell can hold up to 8, and so on. The reasoning for these numbers is a complex and subtle blend of theoretical argument and empirical fitting. He invokes symmetry considerations and the correspondence principle, but the ultimate justification comes from chemistry itself. He demonstrates that his proposed electron configurations for the noble gas helium, neon, argon result in highly stable, close shell structures. The alkali metals that follow them in the periodic table each begin a new shell with a single, loosely bound electron, explaining their high reactivity and similar chemical behavior. The logical coherence of the argument is that of a grand synthesis. Bohr systematically steps through the periodic table, assigning electron configurations to each element and showing how these assignments map directly onto known chemical families and properties, including the transition metals and the rare earth elements. A critical assessment of the essay's internal claims reveals both its immense power and its inherent limitations. The model provides a stunningly successful phenomenological framework. It gives the first truly physical explanation for the structure of the periodic table, a feat that had eluded science for decades. However, the underlying mechanism for why a shell is full with a specific number of electrons remains somewhat provisional. The reasoning feels, at times, like a post-hoc rationalization of empirical chemical facts. The full justification for his scheme would require the later introduction of electron spin and the Pauli exclusion principle, concepts absent from Bohr's 1921 framework. Within the confines of the essay, the strength of the claim rests upon its astonishing organizational success. It presents the periodic table not as an arbitrary list but as the logical, necessary consequence of a single, coherent set of principles governing the structure of matter. It is a work of supreme scientific artistry, pushing a provisional model to the absolute limits of its explanatory power. Conclusion: the collected essays in the theory of spectra and atomic constitution present a compelling intellectual narrative of a theories in motion. The analysis of the work's internal claims reveals a consistent methodological approach, the bold assertion of radical postulates, the rigorous deduction of their empirical consequences, and the constant refinement of the conceptual framework through guiding principles like correspondence. The 1913 essay establishes the atomic model's core architecture through axioms justified by the predictive success with the hydrogen spectrum. The 1920 essay introduces the correspondence principle, a sophisticated intellectual bridge that lends rational coherence to the quantum rules and transforms classical intuition into a tool for quantum discovery. Finally, the 1921 essay demonstrates the model's vast synthetic power, providing a physical foundation for the entire system of chemical elements. The evaluation shows that while the model was a hybrid, a transclassical system, its claims were meticulously grounded in and tested against the spectroscopic and chemical data of the day. Its enduring significance lies equally in its specific achievements and in its demonstration of a uniquely powerful style of scientific reasoning. Bohr's work, as captured in this volume, is a monument to the process of navigating profound conceptual uncertainty with intellectual courage, physical intuition, and an unyielding focus on explaining the structure of the empirical world. It constructed the essential scaffolding upon which the more complete edifice of modern quantum mechanics would later be built.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.